In this video, we will review information about the final project, as well as some tips, hints, and suggestions. In the next section, we will introduce the project description, go into some detail about the different subsystems included in the project, and look at the specification values for this project. To complete this project, you will need to design an analog audio amplifier, which includes an equalizer, volume control, a power amplifier, and optionally, a crossover. We will now detail the purpose and function of each of these subsystems. The purpose of the equalizer subsystem is to adjust the relative loudness of various frequency bands in order to subjectively improve the sound for the listener. This is achieved by separating the audio into different frequency bands, and in each band using adjustable gain so that the frequency band amplitudes can be independently balanced with respect to each other. Once the bands are balanced, they are recombined into a single signal again. The volume control subsystem is used to control the overall loudness of the signal. It's important when designing it to consider the maximum input level of the power amplifier and ensure it won't be exceeded. The power amplifier subsystem provides the necessary power to drive the speakers. Within audio systems, the most common speaker impedances are 4 ohms, 8 ohms, or 16 ohms. So the power amplifier must be able to provide sufficient voltage and current to drive a small load. A single op-amp is not adequate to drive such small loads, so a purpose-built IC is used instead. The LM386N low-voltage audio power amplifier used in Lab 10 is an adequate amplifier to meet the specifications of this project. This circuit has a gain of 20 and can drive a speaker as low as 4 ohms. In this circuit, we have the amplifier connected with this capacitor and resistor. This makes up our power amplifier circuit. This capacitor and resistor model the speaker load that's in lab. The simplicity of the LM386N makes it a great choice for simple amplifiers. The optional crossover subsystem divides the output of the power amplifier into frequency bands for the two speakers. Each speaker is best at producing sound at certain frequencies, so the crossover distributes the power to the speakers best suited for it. The low-frequency speaker, or woofer, will be connected to a low-pass filter, and the high-frequency speaker, or tweeter, will be connected to a high-pass filter. The suggested schematics from the lab manual are reproduced here. The component values for the inductor and capacitor can be computed using these provided equations. The inductance will be equal to the speaker resistance divided by pi times the crossover frequency, and the capacitance will be equal to 1 divided by 4 pi times the crossover frequency multiplied by the speaker resistance. Using these values for the inductor and capacitor will cause the crossover response to sum to be perfectly flat. We will now review the specifications for the audio amplifier design. The speaker resistance is set at 8 ohms and is fixed by the speakers provided in lab. The equalizer subsystem has 3 frequency bands with defined 3 dB cutoff frequencies, at 320 Hz for the low band, from 320 Hz to 3.2 kHz in the mid-band, and at 3.2 kHz for the high band. It can be helpful when considering the wide bandwidth of the middle band to consider that a bandpass response can be achieved by cascading a low-pass filter and a high-pass filter, one after the other. This approach can help achieve wideband bandpass responses. Continuing with the specifications, the voltage at the input of the amplifier with all the equalizer knobs turned to minimum must be less than 15 millivolts RMS at the 200 Hz, 2 kHz, and 10 kHz test frequencies. The voltage at the input of the amplifier subsystem with the equalizer all the way up must be less than 100 millivolts RMS within 10% at the 200 Hz, 2 kHz, and 10 kHz test frequencies. The ripple tolerance is 15 millivolts all the way across the 200 Hz to 10 kHz test band. This means that the minimum voltage and maximum voltage at the input of the amplifier subsystem with the equalizer all the way up across the whole frequency coverage must only differ by at most 15 millivolts RMS. The amplifier output power must be at least 400 milliwatts over the entire frequency band. This visualization shows the RMS voltage at the input of the power amplifier, with the green dashed line showing the nominal 100 millivolt level, and the red dashed lines 15 millivolts above and 15 millivolts below to give some context for the ripple specification. The other plot shows the transfer functions of the filters in the equalizer section, with a low-pass filter for the low band, a bandpass filter in the middle band, and a high-pass filter in the high band. These filters are implemented as ideal with a gain of 1. The middle band is realized using a high-pass filter cascaded with a low-pass filter. These visualizations can help give you some intuition when trying to tune your equalizer subsystem. The issue we see here is that the maximum voltage in the power amplifier input graph at around 1000 Hz is maybe 120 millivolts RMS. You can see that the peak-to-peak voltage ripple here exceeds the specification, so we'll need to decrease it. A way we could fix this is by slightly decreasing the gain in the middle band of the equalizer. When we do this, you can see that we're able to move the total response back within the specification. Here is another possible scenario of trouble. You can see that the voltage to the input is significantly out of the specification. If you look at the transfer functions of the filters, we see that the gain of the low-pass filter has gone down substantially, whereas the gain of the high-pass filter has gone up. To remedy this, let's try increasing the gain in the low band and decreasing the gain in the high band. By doing this, we will see we're able to correct the response within the tolerances. Here is the third example of a potential problem when tuning an equalizer subsystem. You can see here that we have out-of-specification performance at around 320 and 3.2 kHz, the intended frequencies where the bands cross over. If you see a dip where they cross over, this probably means that the two filters don't overlap enough. Conversely, if you see a peak, this probably means that the two filters overlap too much. You can try to fix this by adjusting where the cutoff frequencies are for the different filters. To fix this dip, I'll try to increase the cutoff frequency for the low-pass filter. As I bring it closer to the low edge of the middle band, we return towards the specification. To fix this peak, I'll need to cause the filters to overlap less. To do this, I'll increase the cutoff frequency for the high-pass filter. When I bring them back into alignment, we can see that we've gotten back in specification once again. One point to note is that our crossover frequencies don't overlap precisely at the dashed brown 3 dB downline because we have that decreased gain in the middle band. In the previous section, we went through the project description and the subsystem descriptions. We also went through the detailed specifications for the project. In the next section, we'll review RMS and power concepts, look at some example amplifier calculations, and go over some helpful tips for the successful completion of this project. All of the powers and voltages in the specifications rely on RMS voltage, so it's worthwhile to review RMS concepts. In lab, measurements will be done with sinusoidal test signals, so when we're looking at this simplified schematic, we'll consider a test signal Vs of t equal to an amplitude A times sine of omega t. To find the power in this resistor, we're going to use the expression power P is equal to the RMS voltage squared divided by resistance. It's useful to recall here that for a sinusoidal signal, RMS voltage is equal to the amplitude of the sinusoid divided by root 2. Now, in lab, it can be more convenient to work with peak-to-peak voltages instead of amplitudes. So Remembering that the amplitude will be half the peak-to-peak voltage, we can rewrite this expression as VRMS is equal to the peak-to-peak voltage divided by 2 root 2. Now that we have this expression, we can substitute it in to this power equation. This gives us that power P is equal to the peak-to-peak voltage squared divided by 8 times the resistance R. I will now work through an example of calculating power in a circuit with a power amplifier. In this example, we'll consider a speaker with a 4 ohm resistance. We'll consider trying to deliver 2 watts to that speaker. And we'll be using a power amplifier with a voltage gain of 200. To begin, we're going to use the expression we just derived and get that the power delivered to the speaker will be equal to the speaker voltage, peak to peak, squared divided by 8 times the speaker's resistance. Plugging in for the value that we have here, this gives us that P speak is equal to V speak squared divided by 8 times 4, or 32. Now I'll rearrange this and solve out so that I get the peak-to-peak voltage across the speaker alone. This gives me that V speak peak-to-peak is equal to the square root of 32 times P speak. Now, in the next step, I'm going to substitute in our target power, 2 watts. That will multiply out to be the square root of 64, or 8. So we have that the peak-to-peak voltage across the speaker needs to be equal to 8 volts peak-to-peak. Now, we know the peak-to-peak voltage across the resistor, but what's the input voltage that we need? To do this, all we have to do is divide through by the voltage gain of our amplifier. When we do this, we see that the input voltage necessary will be equal to 40 millivolts peak to peak. Another useful reminder is that buffers can be used to isolate different sections of a circuit from one another. If a subsystem is being loaded by the next subsystem, adding a buffer is a good strategy to isolate them from each other and minimize the loading effects. Op-amp buffers with high input impedance and low output impedance are generally a good choice. Shown here is the detailed block diagram for the audio amplifier system. Applying many of the suggestions given in this video, for example, considering the maximum input levels for the power amplifier when designing the volume control, or using the pre-provided formulas for the inductor and capacitor values in the optional crossover from the lab manual, or furthermore considering using buffers where necessary, should help your designs be successful. In the previous section, we reviewed power and RMS concepts, looked at some calculations with an amplifier, and reviewed some of the suggestions to help improve your designs. In the next section, we'll learn about frequency response analysis tools and how to use them in lab. This device is an audio mixing console. It takes audio from several different sources and combines it to send it to different outputs. If we look at one input channel of this device, we'll see that it has quite a bit of similarity to the audio amplifier system being designed in this project. It has an equalizer subsystem with 3 frequency bands and a volume control section. The power amplifier and crossover subsystems would be separate external components when using this device in a real-life setting. We will be analyzing this system from the channel 1 input to the auxiliary send output. We'll be using this to demonstrate the functionality of the frequency response analysis tools. I'll use this diagram to explain the correct way to hook up a frequency response analysis, or FRA tool. Both the benchtop oscilloscope and the analog discovery use similar configurations to do frequency response analysis. The FRA tool will have 3 connection points: the output of a waveform generator, and connection points for the input of your device and the output of your device. These will be measurement channels, either on the oscilloscope or on the analog discovery. The waveform generator output needs to be connected to the input of your device under test. It also needs to be connected to the input channel of the FRA tool. The output of your device under test needs to be connected to the output channel of the FRA tool. The FRA tool functions by applying a stimulus signal to the device under test and measuring that stimulus signal at the input of the device and at the output of the device. It compares the input and output waveforms to determine the magnitude and phase response of your device at various frequencies. I have made the necessary connections to use the benchtop oscilloscope in frequency response analysis mode. I've connected the output of the wave generator to both the channel 1 input and the input of the audio mixing console. The output of the audio mixing console is connected to the channel 2 input. To access the frequency response analysis tool, press the Analyze key, then use the Features soft key and the multi-purpose knob to select frequency response analysis. Then press the Setup and Apply soft key. This opens up the frequency response analysis configuration menu. Here we'll change the settings for our measurement. The frequency mode by default is in sweep, which is what we want. Now we have to change the start and stop frequencies. We would like to go from 20 Hz to 20 kHz since it's an audio signal. However, the benchtop oscilloscope has a fixed group of points that we can choose for start and stop frequencies. So the closest we can do is from 20 Hz to 100 kHz. 10 points per decade is acceptable for our measurement, and the default source settings, channel 1 as input and channel 2 as output, match what we want. Make sure to change the WaveGen output to high Z mode, and for my measurement, I'm going to configure the amplitude to be 200 millivolts peak to peak. Once you've configured the settings the way you'd like them, press Run Analysis, and the oscilloscope will automatically begin the frequency response analysis plotting. You can see from the plot that's developing that this audio mixing console has relatively flat magnitude response and approximately 0 phase response. There is a large deviation once we get past 20 kHz with a greatly different phase response and a roll-off of the amplitude response, but this audio mixing console was only designed to work up to 20 kHz, so this is acceptable performance for it. I'm going to adjust some of the settings on the audio mixing console by decreasing the gain in the low equalizer band and increasing the gain in the high equalizer band. I'm now going to run the analysis again and look at the effects. First, press the Setup and Apply soft key, and then press Run Analysis again. As the tool begins the plot, we can see that we have less gain in the low frequency region. The gain returns to 0 in the middle frequencies and increases above 0 in the high frequencies. This matches what we expect from the settings changes that I made. In order to use the frequency response analysis on the analog discovery, you need to open the Network module. Here we can make many of the same configurations which we made on the benchtop oscilloscope. We'll set our start and stop frequencies to 20 Hz and 20 kHz for an audio signal. Now we have to choose the number of samples. This will be a balance of number of points on the waveform and detail versus speed of completing the sweep. 20 samples is a good number for this measurement. We also need to change the amplitudes of the wave generator output. This is measured in amplitude, which will be half as much as volts peak to peak. On the benchtop oscilloscope, I used 200 millivolts peak to peak, so here I'll use 100 millivolts amplitude. Now I'm ready to do the frequency response analysis. I'll press Run. You can see that the waveform that's traced mirrors the results that we got on the benchtop oscilloscope. I'll now adjust the scale to make it easier to see the detail, changing the magnitude response scale to plus minus 10 dB, and the phase response scale to have a span of about 75 degrees total. The next thing that I'm going to do is adjust the equalizer, again like I did in the benchtop oscilloscope, by decreasing the gain in the low band and increasing the gain in the high band. Now I'll run the frequency response analysis and observe the results. We can see in the magnitude response, as expected, there's now lower gain in the low frequencies and increased gain in the high frequencies. In the previous section, we learned about frequency response measurement tools and how to use the benchtop oscilloscope FRA and the analog discovery FRA. Next, we will conclude. In this project, you get the opportunity to create your own basic audio equalizer. Many different concepts and techniques that were learned throughout the course of this lab will be necessary to successfully complete this project.